Alright, this is section 1.2, functions and their graphs. First we're going to talk about relations. And here we have our definition of relation. It's going to be a set of ordered pairs. They don't always have to be numbers in our ordered pairs. I know we're used to numbers being in our ordered pairs so that we can graph those. These can be any type of relation as long as they're paired up. Here what we have are some activities and the number of calories burned from each activity. The activities are the first components of our ordered pairs. Those make up the domain. The number of calories burned are the second part of our ordered pairs, and those make up the range. Now notice the braces that indicate that we are talking about sets. And our domain is a set, so it's in braces. We've got all of our activities listed out, and the range is also in braces, and it has all of the number of calories listed out. And notice that it doesn't list 505 twice. Here's an example of a relation, and what we're going to do with this is find the domain and the range. Remember, the domain is what we're going to get from our taking all of the first components of our ordered pairs. So in this case, these are the numbers. Looking at the numbers and the names that go with them, the relationship that I believe is going on here is a temperature for each person. So in this case, our domain is going to be our temperatures. So we'll list that in braces because it's a set. If any of these temperatures showed up twice, the same exact temperature, we would only list it once. There's no reason to list the same number twice in a set. So we have our 98.6, our 98.3, and our 99.1. That is our domain. For the range, we want to list out all of our second components. And we put those in braces to represent that set. So those are our names: Felicia, Gabriella, and Lakeisha. So now we have our domain and range for this specific set. We're going to determine whether each relation is a function. So what we need to do is check. We have 1, 2, and 3 in our domain here. So none of those recur, so we don't have to check. If we noticed that we had a 1 paired up with something besides an 8, it's paired up with 8 in the first one here. If it were paired up with something besides 8 somewhere else in this set, then we would not have a function. So this one works. This one is a function. Now in the second one, we've got 2. It shows up as the first component of each of these. So in our domain, the only number we have is 2. But it is paired up with 3 different numbers from the range. So this one is not a function. And in our third example here, this third set, we have 3, 4, and 5. Since none of our first components recur, we don't really have to worry about it. It is a function. You might be confused that the range is the same. It's a 6. It goes with each of these. That is perfectly fine. We just want to make sure that for each member of our domain, which is our first component, that we only have one number paired up with that for our second component. So since we have 3 different numbers as our first components, 3 different numbers for our domain, it doesn't matter what they're matched up with. So this one is a function. Now we're going to look at functions as equations. And this is also in your textbook, I believe. Most of these things that are that are blocked out in blue you can find in your textbook. And I'm going to try not to read so much of this to you. But anyway, we have an equation here. And just because we have an equation does not mean it represents a function. Just like every set of ordered pairs is not going to necessarily be a function, not every equation will be a function either. So in this case, we've got y equals negative 0.016 x squared plus 0.93x plus 8.5. And the variable x represents the years of working for a company, and y represents the average number of vacation days for each year. So the variable y is a function of the variable x. For each value of x, there's one and only one value of y. So whatever we pick out, any x that we would like, 1, if we want to use 1 n for x, we want to use 10 for x, no matter what we pick for x, we're only going to get one answer for y if we substitute that in. So that makes this a function. And again, not every set of ordered pairs is going to define a function, and not every equation will either. So if we're going to take a look at equations and decide whether or not they're a function of x, what we need to do is solve them for y, because we're looking to determine whether or not these equations define y as a function of x. So if we solve them for y and then substitute whatever we like in for x, if we can only get one answer for y when we substitute some number in for x, then it's going to be a function. But if there ever occurs a time that you can plug in a number for x and get out more than one answer for y, then it's not going to represent a function. So solve this first one for y. You have x plus 4y equals 8. So if we subtract x from both sides of the equation, you have 4y equals, and you can write this as negative x plus 8 or 8 minus x. It really doesn't matter. Now since we're solving for y, we want to divide both sides by 4 so that we get y equal 2, and we can rewrite this dividing each of these terms by 4. So we can write it as negative x over 4 plus, and then a divided by 4 is 2. So we can rewrite it that way. And now when we look at this, no matter what x that we substitute, no matter what number we substitute x in this equation, put in an 8, put in a 2, put in whatever number that you like, you're only going to get one answer for y. Y is going to equal something. But you won't get two different answers for the same number that you put in for x. So that makes this a function. Now, at this point, you're probably wondering, well, when doesn't it work? Well, let's take a look. In this second equation, if we solve for y, subtract x squared from either side of the equation. Now 2y is equal to, again, it doesn't really matter the order as long as you have the sign correct on those, 10 minus x squared, and then divide everything by 2, so that you have y equals. So we have y equals 10 divided by 2 is 5 minus, and we have our x squared over 2. That one will also, no matter what x that you put in, plug in 2 for x. When you solve, you'll only get one answer for y. So that one's also a function. So now we're looking at the last one, which I'm going to do in red and green here so you can see it a little better. If we solve it for y, again, we'll subtract x squared from both sides. So now we have y squared is equal to, it doesn't matter the order of these, as long as they have the correct sign. So y squared is equal to negative x squared plus 16. Now to finish solving this, we're going to have to take our square root. And what happens when we take a square root is we can get the positive or the negative of whatever we have under here. And that's what makes this not a function. Because whatever number that we get for an answer, we have either the positive version of that number or the negative. So if it turned out our answer was 5, it would also be 5 or negative 5, positive 5 or negative 5. So you get two different answers for y, which makes this not a function. What you're going to be looking for in terms of equations, if you're going to look to see if an equation defines y as a function of x, as long as you don't get even exponents on y, like this one has a squared, so it's an even exponent. What happens is you can get the positive or negative version of your square root. Well, the fourth root, it works the same way. You can get the positive or the negative. But all your odd roots will give you just one answer. So if it's y to the third power or y to the fifth power, then it's okay as a function. But if it's y squared or y to the fourth or y to the sixth, then you can have two different possibilities for answers. And that will make it not a function. So now we're going to look at function notation. And what we write is f of x. There's f of x, and that's how I read it. You could read it f at x, but generally I read it f of x. So that's what you'll hear me say. That's what I hear most of the time. But if someone said f at x, that also works. So f meaning function of x, the x is the value put in. So in this case, f of x is equal to, there's your equation, and it has x's in it. We could also write this as a y instead of f of x. You may be used to seeing it as y equals, and it has the rest of the equation in there. F of x and y are interchangeable. So in this example here, we're going to evaluate the function at 10. So what that means is, what we write is, we want to know what the function it looks like at 10. So, well, there's a good example of where you say f of 10 or f at 10. So what that means is, since we have a 10 here instead of an x, in the equation, we're going to put a 10 instead of x's. And that's what they did here. So anytime that you see those, I generally write out my equation, but I put parentheses wherever the x's are. And then I write out everything else just the way it looks in the equation. And then I go back and substitute in whatever number I was supposed to. In this case, it's the 10. And this is a good opportunity for you to try out a scientific calculator. It will have your exponents on there, and it will do order of operations. So it can make some quick work of this type of problem here.